Scotty from right side, right? Taste is this slide, other slides okay, then go ahead. Yeah. This is fine.
ପଛପଟେ ଦେଖାଯାଉଛି
ଶୁଣାଯାଉଛି
that should be there. Just put it.
बिना ये तो शुरू Good morning to all of you. So first of all, I would like to thank Professor Anda for inviting me to this international seminar on very important topics. So as we will be, as we will go on, you will realize that my talk is slightly different from the topic, the recent advances in high energy and transmitter fields. So now my current affiliation is field of Bhubaneswar, but before that I was in Metro Research Center, Institute of Science, Bangalore. Okay, Dr. Jagdish Kumar is also from that place. So, and the mandate of our department, where I was before, okay, June only I came to Institute of Physics in next one. So the mandate of that department was, or is, that we synthesize the material. Okay, this is the Metal Research Center I was in. So we develop the materials, then characterize them, study their chemical and physical properties, and based on the properties, okay, we get a clue that where we can have the applications. And And once we say, for example, able to decide that they're based on the property that will have these applications, eventually go for prototype devices. So that is the mandate of the department. So my talk mainly will focus on the material aspect of resistive sensing. So I will start with few examples that you see. It may not be very recent, okay, but hopefully that will guide. My talk will guide to develop new materials for different applications. And this is also an outline of my talk. So as the title suggests, the resistive sensing. So resistive sensing means we have to measure the resistance. Okay, and from the resistance we can see what kind of sensing we can have. I will start with a simple example. You have a fever, you go to the health center, you go to a doctor, a thermometer is used. Okay, so there is a temperature sensor. The thermometer is simply a temperature sensor. So how you get the temperature? You don't get the temperature directly. If you see there is a liquid, there is a mercury in a glass. As the temperature, body temperature is high, then the level of mercury in the tube that goes up. And as you see this, there are some readings with temperature. And from the reading, so basically the properties which it decides is the height of the mercury. It is pre-calibrated. It's calibrated before that it goes this high, this much high, then this is the temperature. And that's how the doctor tells you this is the temperature. Of course, you can also get to know the temperature. And there is the height. So height is very relative. So in this case, whatever the example I am going to discuss today, that is based on the resistive measure. Okay. So if you know the resistance, say for example, if you know metal, the platinum, say for example, if you go to any lab where the temperature measurement is associated with, so in that case, you must have heard that platinum resistance thermometer is used. Platinum is a metal. As the temperature is increased, the resistance increases. So if you know that this what is the resistance, then from the resistance you can reduce the temperature. So this is one example. So as you see here, the outline topic, I will give the example of temperature sensing, photo detection, and I will discuss the importance of this photo detection and then gas sensing. Okay, how the resistance can be monitored to evaluate the performance of the material actually for different type of sensing. So in case of photo detector, it is a light sensing. You are basically detecting the light. And the material I will be dealing with is SnSe2, zinc oxide, gallium nitride for photo detection, silver, gold and carbon nanostructure for ammonia sensing, and finally actually how this ammonia sensing can be useful for environmental and biomedical applications. So we already know that the resistance of a material, not the resistivity, the resistance of a material depends on length and diameter. R equal to rho L by A, that we know. And as I have discussed, especially for platinum, copper, any metal you take, that if you rise the temperature, the resistance increases. In case of semiconductor, resistance decreases as the temperature is increased. And as I told you, the platinum is used. So I have one example. Yeah, so temperature, so there is variation with temperature, then it can be used for temperature sensing. If the resistance of a material varies with environment, okay, it can be useful for gas sensing. If you shine light to a material and if the resistance changes, that can be explored for photo detection. And if the resistance is changing with pressure, then that can be useful for pressure sensing. So what are the requirements? If you are looking at, so basically the low cost, the material which we develop should be of low cost, it should not be expensive. It should be small, so that you can place the material where you want. It should not be too bulky. To remember, earlier the computer was kind of a big room size, the size of a big room, and now you can see it's so thick. So now we are going for miniaturization. So if you have, you can develop small systems. And construction easily duplicated. Okay, it should not happen that you design once and it's not easy to duplicate it. And then stability over time, so that's called durability. So any sensor, this should be durable. So today it should, suppose 25 degree, you come to this room tomorrow, it should be 25 degrees, it should not be 26 or 27. So durability has to be there, and accuracy. Okay, how accurate the temperature is. So suppose when I say 25, theoretically you can take it 25, but experimental, it can be 25.1, 24.9, whatever. So what is the accuracy if you say 25K? And the range. So when I'm talking about a sensor, okay, like again I go back to the thermometer used in dispensary. It's a very narrow range. Okay, maybe 37, 38. In the lab, what you use, it can go to 800, it can get to 1000 degrees centigrade. So the range, the applicability of the sensors. And the sensitivity, and of course that is related to the accuracy also. Sensitivity means, for example, what is the change in the resistance if I change by 1K? Okay, it should be high or it should be low? What do you think? It should be low. Why? See, the change in the resistance, suppose I change by 1K, 25 to 26, and the change is 0, say for example. Can I use that? So I cannot use that. It doesn't matter what is the temperature, the resistance will be the same. So it should not be too small. It should not be too high also. The dR by dt, the change in the resistance should not be too high. Suppose I take the example infinite. 1K change in the temperature. Suppose it leads to the infinite change in the resistance. That will be a problem in the measurement. Because I have to, for resistance measurement, I have to apply a constant bias, measure the current, or apply a constant current, measure the voltage. If the change is too high, say for example, the range of the voltage, millivolt to say for example, between volt or kilovolt. So in that case also it will not be very good for sensing applications. So it should be moderate, okay. So that's how the sensitivity comes into picture, and it should be easy output. I should be able to explain in this context that if how easily I can measure. See, in the case of thermometer, it is the height. In this case, it is the change in the resistance. Okay, how easily I can measure the resistance in this case. Okay, so these are the few requirements one can look for when you are designing the sensor. And on the top, actually, if the output, or in this case the resistance, what I am dealing with temperature, for example, if it is linear, okay, for calibration I have to know the R versus T curves. Okay, so once I know the resistance, I should be able to reduce the temperature. Okay, so if it is linear, it is easier to find out the temperature if I know the resistance. So this is a kind of a very well known or commonly used sensor, platinum 100. Okay, what is the lab we use? That is a PT100, and it's called platinum resistance temperature detectors. RTD means resistance temperature detectors are the most common type, and it is an excellent correlate resistance, and the range is -260 degree to 850 degree centigrade. So in that range, this platinum resistance thermometer can be used, and the accuracy is like 0.1 degrees centigrade. Okay, and the number 100, the PT 100, that basically denotes the 100 of the resistance of the platinum wire which is used is 100 ohms at 0 degrees centigrade. Okay, this is a question generally asked in an interview also. Okay, so that 100 denotes for that 100 ohm at 0 degrees centigrade. There are also platinum 1000. So in that case, the resistance of platinum is 1000 ohm at 0 degree centigrade. Okay, this is a wire. This is platinum 100, and platinum 1000 is a thin film. Okay, when the thickness is reduced, the resistance can be increased. So that's how it is designed. It basically is based on platinum thin film. And this is how the resistance versus temperature curve of a platinum 100 looks like. And you see from 0 degree centigrade to 900 centigrade is almost linear. And the sensitivity is something like 0.4 ohm per K, and accuracy is better than 0.1 degree centigrade. Okay, so that's why it is commonly used in this temperature range. So for your information, the other temperature sensor which is used in the lab or in the industry is basically diodes. Okay, diodes, you know, is a PN junction. Silicon, gallium arsenide diodes are used.
Those are 100 graphs or so. Below 0 degree, there is.
Which one?
This is degree Celsius, yeah.
Degree Celsius.
Okay, no. Below.
That also linear up to minus 260 degree.
Minus 260.
Yeah.
I see.
After that, it is basically the sensitivity goes down.
Like things like, suppose we want to measure transistor temperature, superconducting material.
Yeah.
Do they use this kind of?
But in that case, silicon generally used. But if it is like high DC superconductor, this can be. If it is high DC superconductor, this platinum 1 level can be. I put it like this, minus 260 degree. Can be. And below that, of course, the sensitivity goes down. Yeah.
Still it is linear.
Up to 260 degrees linear, minus 260. Beyond that, it basically if you look at RT curve, it goes like this. Okay. Yeah. So diodes, thermistor just again the resistance based. Thermocouples, you know, it's also used in the laboratory. Bimetallic stripes, there is an interesting system. It is basically two metals, up to like you know. One example is, for example, stainless steel and brass. Okay, you fuse them together, and the linear expansion, the thermal expansion coefficients of both the systems are different. And when you heat it, one system will expand more than the other system, and accordingly it will bend. And the bending angle will give you the indication of the temperature. Okay, and in the flight, okay, basically we don't get to know in domestic flight, but if you are traveling internationally, like as you, especially during the landing, they show the height versus temperature. This is the height, this is the temperature. Okay, so bimetallic stripes are used at different places of the wing and the aircraft to monitor the temperature. So this is actually an interesting system from that point of view. And liquid in glass thermometer, that is basically your mercury in glass. Or alcohol, there are, you know, in the labs, some labs, we can go up to 100 degrees centigrade using liquid, it's an alcohol based thermometer. The principle is similar to or identical to your mercury glass thermometer. And there are also luminescence thermometers. By monitoring the luminescence properties of material, one can monitor the temperature. So this is just to give you some idea about the thermometers, different thermometers actually used. But as my talk deals with the resistance-based thermometry, also resistance-based sensing. I mean the platinum, that also based on the resistance. Now I take you another systems like photodetectors. So photodetectors are basically also photosensors. So it's basically sense light and all of other electromagnetic radiations. And photodetectors mainly rely on the photoconducting properties. Okay. So few examples like your smoke detectors we use nowadays. Okay, nowadays probably all new apartment and all these places, okay, are important places. We have smoke alarms or smoke detection. So basically, it consists of a IR LED and a photodetector. Simple. Okay. And this is the design that you see here. So the photodiode is then you see off center, and once you have smoke, that IR light, okay, emitted from the LED, that gets scattered and it falls on the photodiode. So the current increases, photocurrent increases, and then that signal is processed to the alarm system, and you get the sound. Same thing. I mean, this image is not clear. And if you are a cricket lover, you will be wondering actually. Okay, the instrument used to monitor the light intensity. The umpire uses basically a photodetectors to see whether the condition, the light is enough to continue the play, or the play is to be stopped. So there also a light, the photodiode or photodetector is used. Okay. Similarly, if you are dealing with atomic force microscopy, okay, so there are a laser light falls on the tips, the cantilever, it falls on the tips and gets scattered. If the surface is smooth, actually it is adjusted as such a way there are 4 diodes or 4 photoconductors. Okay, and they cancel each other so that the photo current eventually will be 0. 4, so 2 will be plus and 2 will be minus, so that you get a photo. The photo current should be 0, but if it is bent slightly, then it basically that light spot get off center. Either it will be more on A1 or A2 or B1 or B2 depending on how it is getting reflected, and you get a photo current. Okay, so there also read photo detectors. So there are so many applications of the photo detector, and also the technology looks like mature if you look at. Okay, technology looks like mature because you are using on a daily basis, but still there are probably rooms for improvement. And if you can understand the principle behind the operation of these photodetectors, probably we can improve it further. And also research is on if you can design a new material. So for example, for IR detection, silicon is a major technology. Okay, silicon can be used. But suppose tomorrow there is scarcity of silicon. We should have another material with a similar performance or a better performance so that easily you can replace the silicon. Okay. So that's why we need to understand what are the problems associated with photodetectors, what are the figure of merits, how we can improve them, and all these things. So again, if you look at the literature, these are the materials and these are the spectral range. So this is the 0.7 micrometer to 2.7 micrometer. If I have to detect, then I can use indium, gallium arsenide based photodiodes. If I have to use 1.1 to 1 micrometer to 3.2 micrometer, again this is for IR, then I can use lead sulfide. Similarly, these are the range and these are the materials we can use. And for UV detection, we can use zinc oxide, gallium nitride, silicon carbide, diamond. So these are the materials available actually, or if you go through literature, you can find these materials having exploited for UV detection. And after the discovery of graphene, and of course the chalcogen 2-dimensional systems that are being explored vigorously for IR detection. So if you look at, there are mainly two types of photodetector. One is linear, and another is PN junction based. when I'm saying linear, you just simply suppose you take like lead sulfide. Suppose I want to have IR detection. I take lead sulfide and put two contacts, and it should be ohmic. Okay. In that case, the IV curve should be linear. Metal, semiconductor, metal. Okay. I have to take two contacts. So metal, semiconductor, and metal. So that's why it's called M linear device. And the PN junction, you know, like silicon, if I have to use, I have to dope P-type, I have to make it P-type, I have to make another type, sandwich them, and then I get a diode. Okay, I get diode characteristics, and that can be used. So each one has some advantages and disadvantages. The linear device is very simple. The principle, as you see here. So ohmic electrodes, that is metal. This side also ohmic electrodes, that is also metal. In between we have the semiconductors. Now when you shine light, you generate electron hole pair depending on the wavelength of the light and the band gap of the material. Lead sulfide, the band gap is 0.4 electron volt, so that it can be used in NIR, or infrared region. If it is zinc oxide, the band gap is 3.2 electron volt, which is in the UV region, so it can be used for UV detection. So the band gap should be smaller than the light which I am irradiating. Okay, so that when the light is irradiated, you generate electron hole pair. So electron from the conduction valence band goes to the conduction band. Okay, and what happens? Then of course you have to apply bias as indicated there. So hole will be dragged towards the positive electrode, and electrons will be dragged towards the. So electron will be dragged towards the positive electrode, and hole will be dragged towards the negative electrode, and that gives you a current immediately. And remember that the holes in the valence band and electrons in the conduction band, they contribute to the electricity. The electron in the valence band doesn't contribute. So initially you have some resistance or some current if you apply bias. Now when you shine light, you are basically generating electron hole pairs, electron in the conduction band and holes in the valence band, and now you apply a bias. So they drag towards the opposite electrodes, and that's how you get a current which is called photo current. Okay, so the photo current in principle should be very high. Okay, for a good photo detector. And of course, if you look at the textbook, the transit time of the carrier depends on the length of the semiconductor, divided by, you see, mu grid, that is the mobility of the charge carrier, and the applied electric field. So what it tells us that the transit time of the electrodes, the charge carrier, can be tuned, okay, by varying the length, so the distance between two electrodes, the mobility of the charge carrier, which is the intrinsic to the system. Lead sulfide has different mobility, zinc oxide has different mobility, silicon has a different mobility. Okay. However, we can tune L and E. E is the how much electric field we are applying. Okay, that is in our hand. But overall, we can tune the transit time. I will come to that why it is important. However, in case of a PN junction, okay, then the equation which is similar to the previous linear devices, but in this case the only difference is that the L is replaced by W. The length between the electrodes is replaced by the depletion width. Okay, and the depletion width is in nanometer. However, in the previous case, the distance between two electrodes can be millimeter, can be centimeter. If you can design, okay, it can be in micrometer also. Okay, you can have nanometer, but you have to be really careful to have two electrodes, okay, separated by a 9 nanometer distance. It looks, maybe it's possible nowadays, it looks very promising that yes, the L of a linear device can be, made nanometer range, but experimentally it has a lot of challenges. Okay, when you try to put two metal contacts between with a separation of few micron, then they get basically touched. And as you know, the electron pass through less resistive path. In proper, when the two electrons get in contact, then electron pass through the electrons only. You don't see the presence of the silicon or the semiconductor. So there are a lot of challenges in case of linear device. Actually, when you want to put two electrodes with a separation of few nanometers, but if you have p-n junction, the depletion width can be reduced. Okay, or generally it is in nanometer range. So if the response time or the transit time in case of linear device is, for example, in second, we can have millisecond or picosecond in case of p-n junction. Okay, so the response time basically, which is a crucial figure of merit for a semiconductor, we can make it in the picosecond range or nanosecond range by fabricating a p-n junction. And in this case also, the mobility, the individual potential, everything basically can be tuned to have the different tune the transit time. So there are different figures of merits. So one is the response time, okay, which is correlated with the transit time, and the sensitivity. Sensitivity is defined of a detector. So in case of resistance thermometer is dR by dt, that is the sensitivity. Okay, the change in the resistance for 1 degree change in the temperature. So in this case, the sensitivity is I photon by I dark. Okay, so when I am talking about, here I am talking about the photocurrent, I am talking about the resistance. But you can always correlate the photocurrent, the dark current with the resistance because your applied bias is constant. Okay. When you are not applying or irradiating the sample with any light, you have some resistance. Okay, that is a dark. There is a resistance in dark, or if you are getting a current, there is a dark current. Okay, this is how it is represented here. And when you shine light, you get a different current. That is a total current. So total current is nothing but dark current plus the photocurrent. Okay, you cannot separate otherwise the photocurrent unless you deduct the direct current. It's a dark current. Okay, so you just completely dark the room, take the measurement. You apply a bias, note down the current. So there is a dark current. Now I expose it to the light. I will get a different current. And I expect the current should be higher than the dark current. Okay? And the photocurrent is nothing but the total current minus the dark current. So in principle, if you look at the sensitivity at the denominator and photocurrent in the numerator, so the dark current should be as low as possible for better sensitivity. And photocurrent should be as high as possible. Okay? Similarly, there is another figure of merit called responsivity. That is the photon, I photon, photocurrent divided by the power of the light, okay, and the area. Okay, when I am shining light, it is falling on the semiconductor, whether it is falling on 1 millimeter square or 1 centimeter square, that also you have to take into consideration. And of course, finally the external quantum efficiency, that is NE, is the number of electrons you are generating or the charge you are generating per number of photons you are irradiating. So that decides the external quantum efficiency of a photodetector. So for fast response time, that depends on, as we have discussed, that on electron separation, depletion width for photodiodes, mobility of the semiconductor, and high sensitivity or responsivity and the external quantum efficiency, that depends on the low dark current and high photocurrent. So these are the things I have already discussed. So for high photocurrent, generally you have to suppress the charge carrier on recombination. That is one of the important things actually in semiconductors. So what I mean, say for example, when you shine light, and of course you apply bias to drag the charge into opposite directions. Okay. When you are shining light, you are shining not at in a kind of 1 millimeter square, for example. So that from 1 millimeter square, electron from here, suppose I have the positive electron this side, electron generated from here will go towards the right hand side, and goes from this side goes to this side. In between they see each other, and then there is a chance of recombination. And once they recombine, you don't get a free charge carrier, so your current gets reduced. So one needs to basically suppress the charge carrier recombinations. Okay, I'll give an example of how this can be done. So before that, we have dealt with a SnSe2 nanostructure thin film for IR photon detection, because the band gap of this SnSe2 system is 1.2 electron volt, and the mobility is 100 centimeters square process divided by volt per second. The band gap is good, but the mobility is not that great compared to other semiconductor system. But then we thought, let's explore this, how this is going to behave.
Yeah, what range of temperature at the back of your mind you have?
Basically room temperature. When we're talking about the photon detection, it is the room temperature. Room temperature. Okay. Because the performance will be different at different temperatures. Yeah. So especially for photon detection, we are dealing with the room temperature. So probably I will skip this, but we have just synthesized SnSe2 systems, a thin film. We just spotter thin. You can use a vacuum evaporation system also. Take thin and evaporate it, and then use a simple system like this. You take selenium powder here, place the earlier deposited thin film here. Keep this at 300 degrees centigrade, keep this at 450 degrees centigrade, and introduce an atom flow. You will get a SnSe2 thin. So basically, SN thin films, when Ac vapors goes and interact with Sn, it gets converted to SnSe2 thin. So this is some characterization. This is XRD, this is XPS. This tells us that we have the formation of SnSe2. And there are some clear image, and you see here there are some layered structures. Okay, for SnSe2, it's a layered system like graphene. Okay, and the distance between two layers is around 0.64 nanometer. So some places you can see it is 0.62, and some places it is 0.64 nanometer. So what is important here? If you look at, okay, I am taking the example of this thick film. But by changing the thickness of the film, as you can see, the band gap can be changed. Band gap will be tuned. For 1200 nanometer, it is 1.2 electron volt, as reported in the literature. For bulk SnSe2.
What about those two lines?
Which one?
The 0.6 nanometer apart.
That is basically between two layers. One SnSe2, another SnSe2 layer.
SnSe2.
So between these two layers, this is a kind of a van der Waals material, okay, like graphene. So here also you have SnSe2. So between these two layers we have 0.64 nanometer.
Okay.
But when you are plotting the slope here,
Which one?
the slope, how do you fix the slope?
This one?
Left now. Yeah.
Okay.
The slope you have to get,
Yeah.
but that can be,
No.
you cannot fix these things.
No, you see that where it was linear.
I see.
No, even linear you can have the.
But there is a small range. Okay. You see, if you are talking about that, you can always fit like this. That's what I meant.
Yes, or the
Yeah, yeah.
slope will be little.
No, see, this is basically, one can think about, the right way to put it, if you plot the derivative of that and this, and see where you know maximum. Okay. So this is basically you can do if you are the beginners. But if you are the veteran, you can realize that okay, if I plot this, I can get the. So this is how it is. And of course, you can always get a plus minus.
So it depends upon which range of h nu you are considering, and and the corresponding linear.
Yes, yes.
So that will define the linear, right?
Ah.
For example, the block curve, if I am between say 2.5 to 3 eV,
Yes, yes. Then you get the maximum. If you better plot the derivative.
but this part can I fit it a linear curve from say 1 to 2?
Ah. 1 to
2. It's also kind of
yeah.
linear.
No, where we will get the maximum. That's the basically the right approach actually.
I see.
If you are a beginner.
But in that case, the top one, you can do a maximum there also in the top one. In the top one.
1200 and
1200 one.
where you want to put?
Upper side.
The slope will be low. Okay, that's the first thing. And this will be basically you cannot have two bandwidths.
So you are interested in the proportional resistance. Proportional resistance.
Linear, especially if it is not linear, you can do doesn't have to be alpha. That you can y-axis, divide by d-axis and see where is the maximum. Then you can take that as a bandwidth.
So that you calculate arithmetically or just observe and
Which one?
so this which area to select,
Pardon?
which area to fit basically. So
Then
then
that's what I'm telling you. If you are beginning,
He is a veteran. He just sees it like that.
so basically arithmetically can also be done. We take derivatives.
derivative you can take, you can do that. That's not true. You can do that.
So you are doing basically by observing through eye.
Yes. And actually, as I told you, there can be few percent of error also in that. Okay. So band gap is we have 1200 nanometer film is like 1.2 electron volt, and we have done all measurement. We found that the carrier mobility is much lower what is reported in the literature. It is 100, we get this 8 centimeters square versus divided by 4 second. And it behaves like n-type, and the carrier concentration is 10 to the power 70 centimeters. So then we take two contacts like chromium and aluminum is a gold. So it behaves like you see the IV curve is linear. Okay, the dark one, the lower one curve is the dark one, and then once you shine light, like 1064 nanometer, okay, that is in the iron region. So, and of different powers, you can see there is increase in the current. So, and this is the typical curve generally obtained for either photodetection or gas sensing. And this is called temporal response curve, the photocurrent versus time. Okay, what is done? You shine the light, you take your device, pass apply bias, measure the dark current. Now you shine the light, then there is an increase in the current, and then now you take it out, then there is a drop again. Okay, now you shine again, it increases again switch off like that. So that is basically called on-off curve or temporal response curve, and how fast your device is responding. So that is basically your time that is related to your transit time or the response time. Okay, and once you turn off the light, then how fast is coming back to the dark current. Okay, so this is how it is looked at it. So the response time is quite important. You don't have patience to wait. Suppose the photocurrent is very huge, but it takes 1 hour to come down. Okay, so then also it is of no use. You can't wait till 1 hour to have another measurement. Okay, so the response time will be very fast. And this is how either you can fit exponentially. Okay, the response time or recovery time is exponential decay, and there is the exponential rise. So when you shine light, there is exponential increase in the photocurrent before it saturates. Similarly, when you take it out, then there is a decrease in the photocurrent, and that also is decreasing exponentially. So you can use the exponential fitting and find out the response and recovery time. So these are the response and recovery time for this SNHC2 based device, linear device. 7.76 seconds, that is the response time, and recovery time is 7.52. At 10 volt, 2.5 and 3.7. See what it means basically, as you increase the applied bias, the response time is much faster, which is in accordance with the equation. The transit time is equal to length, and so overall the response time decreases with increasing applied bias. And one can also do the other studies like electron separation, especially for this device, to prove the dependency of the length of the electron separation. So then we switch to an extrinsic approach for achieving fast response. So in that case it is second. You see this is in second, 7.76 and 7.52. So we thought how we can increase the response time or make it faster. So the linear device, as I have mentioned, the length can be in millimeter or centimeter. But in case of photodiode, if I design a photodiode or fabricate a photodiode, the depletion width can be in nanometer. So from my millimeter to, if I can reduce the W, or I can have the W in nanometer range, then the response will be much faster. So keeping that in mind, what we did, and as I have mentioned earlier, that SNSE2 behave like N-type. So how I can make it a junction? So I have to deal with a p-type material. So then we realized that paddock PSS is a p-type polymer. So we took the film, SNSE2 film, and one part we kept free, and a part of this SNSE2 film we covered with paddock PSS. And now instead of taking two contacts from SNSE2, we have taken one contact from SNSE2 and another contact from paddock PSS. Okay. So the paddock PSS and SNSE2 should behave like a PN junction. Okay. And then we realized that, we look at the literature and then we found that mobility is, as mentioned here, and Na is this much, and we estimated the W and then it is 486. Okay. So in principle, if we establish a PN junction between SNSE2 and paddock PSS, we should be able to get fast response. And also it should be a rectifying behavior. It should exhibit a rectifying behavior. But look at the IV characteristic, it exhibits a IV characteristic non-linear. So if you look at minus 200 is around 500 nanoampere, but whereas this is around 600. There is a slight asymmetry. So it basically is not a perfect PN junction. Okay. It's not a perfect PN junction. However, when we shine light, as you see here, this is a dark current, and when we shine the iron light, there is a current. Okay. If you have, if you have come across the photovoltaic cell, you get a photocurrent at zero bias. Because when you shine light, there will be inbuilt potential. Okay, and that inbuilt potential attracts the electron hole pair or electron hole towards the opposite sides, and you get a photocurrent. So keeping in that mind, people have talked about cell power photodetection in case of PN junction. I don't have to apply a bias, but still I get a current, photocurrent, as you see here. Okay, which is not possible in case of a linear device. You have to apply a bias. So the beauty of this device, the PN junction based device, is that you can have cell power photodetection. So basically you are able to eliminate your power supply. Okay, that's what people have also done. But when you'll be wondering, because when there is no current, no bias, the current should be zero. So in that case, the sensitivity, which is the I photocurrent by I dark, how you define it? Okay. But when you don't apply a bias also, you get a very, very small current. And that is considered a dark current. Even if you don't apply a bias also.
This red curve is the difference between the photo and the dark.
No, that is a total current.
Total
That is a total current.
current. So near the bias becomes bias of say 10 MV.
Here,
Around that,
that,
the sensitivity is not so good.
no. So generally in case of photodiodes, it is operated in a reverse bias, not in a forward. Or in a photovoltaic. Okay, and especially as I mentioned, at zero bias, probably we can have maximum sensitivity. Because the dark current will be very, very how. And this is how the temporal response curve looks like. Again at zero bias. Okay, and this is at minus 2 millivolt. But overall, the important thing is that in this case, the response and recovery time is very fast. I mean, at least faster than the linear device. In that case, depending on the bias, 5 volt if you apply, it is 7 seconds. If you apply 10 volt, it is 2.5 or 3 seconds. But here, without any bias, as you see here, you can have 1.33 and 1.2 seconds. Okay, so little bit faster than the previous one. So what is the problem with this? Why I mean? So we are not able to, even though I was expecting the response time can be increased or enhanced much faster, but that did not happen. So then we realized. So you see here, the mobility is very low.
Now, what is desirable? Response time should be small or fast?
It should be fast.
Fast.
Like I turn on the, say for example, light, it should be very fast.
Yeah, that's what I mean. So why it is a problem that you are telling that you want to make the response time larger?
No, I want to make it fast means I should go towards picosecond. Okay. So where the response time is in the case of camera suppose, the response time should be picosecond. Okay, but then most of the devices you see here, except the silicon, select silicon is picosecond. Okay, and all the devices, if you look at the wavelength, okay, if silicon, for example, what is the problem with silicon? Like I told you, maybe tomorrow there is scarcity, but beyond that top, silicon is used for IR detection. It cannot be used for UV detection. Okay, but for UV detection, I have to have another set of material. Okay, like people are exploring zinc oxide, because the band gap is 3.2 electron volt. Gallium nitride again 3.2 electron volt. Silicon carbide around 2.8 electron volt. So that is in the UV range. Okay, so that material can be useful for UV detection. So, but we have to look at, actually that's what I say, we have to understand what are the parameters or what are the factors that is going to influence, so that influences the figure of merits, the response time, sensitivity, all these things. Okay, this is one approach to find out, so because earlier people were mainly focusing on the sensitivity or responsivity. Nobody was bothering about, say for example, the response time. Okay, so we the first probably, if I do the direct myself, that to prove, okay, what are the parameters which is influencing or which are actually influencing the time constant of the device. So then, in this case, the mobility of Paddock PSS. It's a p-time material and it is available, so we got it. We bought it and put a layer. It is quite easy. So that's how we did. But then we realized that we are not to the expectation. So then how we can handle this? So what we did, we look at again these equations, the mobility, and say for example the concentration, okay, and then we realized that silicon can be a material, p-type silicon, so that is also available commercially. We don't have to, deal with it, silicon and dope it, it is available. In fact, we support it, and then we deposited SN2 on p-type silicon. Okay, because the mobility of, as you see, so this is the mobility of Paddock PSS, and this is the mobility of okay, and the response time is dependent on 1 by mu. If you remember the couple of slides. we discussed in the beginning. So in that case, you see there's a huge difference in the mobility. So probably we can now go up to nanosecond or picosecond. So that's how we did. We deposited SnSe2 on silicon, and then we study the time constant. I will skip this. The bottom line is that now we can go up to 57 or 30. So response time is 57 microsecond, and recovery time is 34 microsecond. So by tuning or playing with the the mobility of the counter semiconductors, my SnSe2 is fixed. By playing with the mobility of the counter electrode, I am able to tune basically the response time or recovery time of the device from second to microsecond, which is 10 to the minus or 10 to the 6 times much faster. So this is how it is. So the story basically tells you that yes, it is possible to tune the response time. And I have not discussed rigorously that if the response time is fast, the recombination time will be, the chance for recombination will be low. So you may get higher photocurrent. This is how it is. So what I discussed so far is basically the IR detection. Okay, I dealt with photocurrent, but the photocurrent can be related to the resistance change. Okay. So similarly, zinc oxide is for UV detection, and as you see, I have listed different materials for UV detection. So back on the band, if you look at, zinc oxide can be one of the best materials. But the problem associated with it is that, and if you are familiar with the exciton binding energy, the exciton binding energy of zinc oxide is 60 MeV. Okay, whereas that of gallium nitride is around 25 MeV. And what is the room temperature? 300 K. And if you convert 300 K into MeV, it is coming around 26 MeV. Okay. So you can separate that. But once they see each other, there is a good chance that if you get a zinc oxide, they will recombine much faster because the binding energy between them is 60 MeV, and which is higher than room temperature. In case of gallium nitride, it is 25 MeV, just it is close to the room temperature. Okay, so the chance of recombination in case of zinc oxide is much faster. So how we can handle this? But if you look at the band here, the band of the zinc oxide, the visible range, the wavelength of visible range is 380 nanometer to 750 nanometer. Okay, and zinc oxide is around 390. Okay, beyond 380, it will be UV. So very close to that border, the band gap of zinc oxide lies. So that's why it is one of the best suited material for UV detection. But the disadvantage, as I mentioned, that there is a chance of recombination, they will recombine. Okay, the room temperature is not enough to dissociate them. So then, and another problem associated with zinc oxide is that if it is exposed to ambience, the oxygen, gets attracted to oxygen. Or zinc oxide has the affinity to attract the oxygen, and which is a slow process. Okay, like if you simply talk about the semiconductor, if I shine light, immediately I should be able to generate the electron hole pair, and I turn off it, immediately it should stop, the photocurrent should be zero. But what happens in case of zinc oxide? There is oxygen adsorption, and oxygen has the tendency, because the electronegativity of oxygen is such that it has the tendency to take the electron from zinc oxide. And it is a slow process. The adsorption of oxygen is a slow process that you can see the current drops. Okay, so the response time is really very slow in case of zinc oxide. I'm not going to deal with that in this context, but what we have done in this context is how we can separate the recombination of charge carrier, or how we can suppress the recombination of charge carrier. So this is we have deposited zinc oxide again, but what we have done afterwards, as you see here, we have taken carbon nanotubes. So this is basically the zinc oxide thin film connected with two contacts, silver contacts. Okay, apply a bias, get a current, and you see the photocurrent. And now we have actually sprayed carbon nanotubes. Okay, over the zinc oxide, one side of the zinc oxide film, not completely, one side of the zinc oxide film. So in that case, we are able to enhance the photocurrent manifold, maybe 10 to the 3 times. How it happens? So you shine light, UV light, it generates electron hole pair, the zinc oxide generates electron hole pair. Then what happens? The electrons goes to the conduction band of zinc oxide, and then if you look at the conduction band and the Fermi level of carbon nanotube. Okay, it is below the conduction band of zinc oxide. So once the electron goes there, they get transferred to the carbon nanotubes, and through carbon nanotubes they go to the other electrons. Okay, so the charge of the recombination of the electron hole can be suppressed or can be avoided by just following another path. Okay, to the zinc oxide or to the electrons. This is how the concept is very simple. Just you spray it with the synthesis. You don't have to you have to have CNT. You choose another material where you can see that the electron from zinc oxide jump into the system and go to the electrons. So that's how it is. Very simple. And by that we are able to, you can see increase the amount broadcast. You can see the increase the photocurrent. So, how much time I have? I can 5 minutes. Okay. Quickly I go to that. Then there are some more results on photo detection. But since I have also talked about the gas sensing, again, this is interesting one. The chemi-resistive sensor is a material that changes its electrical resistance in response to the changes in the nearby chemical environment. So, for example, this is an interesting concept. I will skip this. Maybe this is an interesting slide. Okay. I'm talking about the gas sensing means H2S. Okay. H2S can be monitored to find out whether you have this problem or not, halitosis. Okay. You can just examine or analyze the breath. Okay. Then you can see the level of H2S is less than 100 ppb in axial breath of a normal human being, where it is more than or greater than 1 ppm, so more than 6 times for people suffering from halitosis. Okay. And similarly, you can monitor the acetone. So the level of acetone is, for example, less than 0.9 for a healthy person, and where it is more than 1.8 ppm for people suffering from diabetes. So just to analyze the action, then you can look at whether you have the halitosis problem or a diabetes. So this is, I have given you 2 examples of the, how important it is to monitor the gas in our axial breath or in an environment. So there is suppose some industry where they are releasing ammonia. Okay, so we need to evaluate. We need to study that how much ammonia is being released in, say, for example, in some industry. So then you need a gas sensor. So like in the other case, like photo detection or resistance thermometer, in this case, so the change in the resistance can give you the concentration of the analytes you are dealing with. So I'll skip this and I will discuss about this slide. This is an interesting slide. And hydrogen detection. Suppose hydrogen is getting released. Or ammonia. And the commercially available, the sensor, if you want to go to the market and buy a hydrogen sensor, it is basically a tin oxide. Okay, tin oxide based thin film based sensor. But it operates around 250 to 300 degrees centigrade. like, he asked me that whether what is the temperature you are dealing with when you use the photon detector, that is room temperature. But in this case, the temperature is around 250 to 300 degrees centigrade. Okay. So, what happens at that? Tin oxide, it behaves like a semiconductor. If you look at, of course, the band gap is around 3.6 electron volt. You can always argue that it's not a semiconductor, it can be an insulator. I will not deny that also. But if you look at, it doesn't matter whether it's an insulator or a semiconductor, the resistance versus temperature curve. Okay, you know it decreases with, the resistance decreases with increasing temperature. And as you see that the rightmost curve, that is R versus T. Okay. So the resistance is decreasing as the temperature is increased up to 150 degrees centigrade. But something interesting is happening, or unusual is happening beyond 150 degrees centigrade. It is taking a U-turn, right? It is coming down and going up. Okay. But what we were not able to see is that the experiment was performed in oxygen atmosphere. What we deal with in the textbook, even though it is not mentioned, when they talk about the resistance versus temperature, metal of temperature versus the resistance versus temperature of semiconductor, okay, it is basically, it is either in inert atmosphere or in vacuum, not in oxygen atmosphere. If you do the experiment in oxygen atmosphere, something unusual may be seen. What is observed here? R versus temperature up to 150. The experiment is performed in oxygen atmosphere. So as we pass the oxygen, as we raise the temperature, the resistance versus temperature is decreasing. Beyond 150 degrees centigrade, what is happening? The oxygen, see here also oxygens are absorbed on the surface of zinc oxide, but those are freely absorbed. But once it raises, the temperature rises beyond 150 degrees centigrade, it's chemically absorbed. So and oxygen has a tendency to take the electron. That if you look at the negative, it is on the right hand side of the periodic table. So it takes the electron from zinc oxide. It's a tin oxide. Doesn't matter, the principle is same. If it is an N-type material, okay, N-type, the conduction is through electron. Okay, and zinc oxide, so the oxygen sucks the electron from zinc oxide. So the number of charge carriers go down. So what do you expect to the resistance? Resistance should increase, and that's what is happening. Okay, that's what is happening beyond 150 degrees centigrade in oxygen. As I have mentioned in the before, that the tin oxide based sensors operates around 250 to 300 degrees centigrade. Okay, so that's why you need a high temperature. You need a high temperature. High temperature is not like 700, 250 to 300 degrees centigrade. Okay, beyond there will be a structural transition, structural transformation. You may not get back your initial state. So one should not go beyond 300. But between this range, it operates. One has to operate between this 250, because below 150 degrees centigrade, as you see, the resistance is same. Doesn't matter whether you take inert atmosphere or in oxygen atmosphere, the resistance is not going to change. So in that scenario, it is futile to use this area for sensing applications. So beyond 150 degrees centigrade, there is a term, and now I suppose I allow to pass hydrogen or ammonia or any reducing gas. Okay, that reducing gas will interact with oxygen, and it takes away the oxygen out from tin oxide, giving back the electron. So if I say, for example, do this study without oxygen atmosphere beyond 200, suppose I expect the resistance here because it is decreasing. Okay, and if you expect it to decrease, suppose the resistance is here, because of the oxygen I have this resistance. Now I pass the reducing gas. So once the reducing gas takes away the oxygen, giving back the electron to the tin oxide, the resistance will drop down here. And the change in the resistance that gives you the indication of the concentration of the reducing gas. Okay, so that's why now probably it's clear that why we need a moderate temperature for clean oxide and what is the principle. So you have to pass the oxygen constant. You have to pass oxygen and then you expose it to the gas which one would detect. So this is how it is for clean oxide. Now we are aiming for room temperature applications. How the room temperature, okay, without going to the moderate temperature, is it possible to have this kind of application at room temperature? Now our research is going on. So in our group we have dealt with nitrogen of carbon nanotube. Okay. Now we have graphene. Now you have carbon nanotube. Just you roll the graphene, you get a carbon nanotube. Now imagine, so you have hexagon, carbon, 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 carbon. So now you replace one carbon by nitrogen. And as nitrogen is more electronegative than carbon, then it attracts the electron. So N becomes a minus and we have surrounding C plus. And when the oxygen, you allow the oxygen to pass through this nitrogen or carbon, then there is simulation results that the oxygen becomes slightly negatively charged. And then oxygen preferably comes and sit on C plus. And again it has more electronegative, so it sucks electron from nitrogen through carbon. This is how it is. And the conductivity changes, or the resistance changes. And now again you do the same exercise. You need to pass analytes of the reducing gas. Okay, you get back your resistance. In oxygen, in presence of oxygen, we have one resistance. Now you pass the reducing gas, we have another resistance. Again, in this case also, the change in the resistance is going to give you the concentration of the reducing gas present in the system. Only difference here is that this is possible at room temperature. And to some extent we have achieved that. Okay. And because of shortage of time, I was not able to discuss that. Maybe I'll find some occasion sometimes. Okay. Maybe to
more elaborate
discussion. More elaborate discussion. Okay. I hope whatever I wanted to communicate to you, you have received it. Okay. And you have, you have not received also, probably you can write out a mail if you have any doubt. Okay.
Questions?
Yeah.
So, in case of platinum 1000, you said that the platinum has 1000 resistance at 0 degree Celsius.
1000 ohm. Yeah, platinum.
1000 ohm resistance at 0 degree Celsius.
Yeah.
But as platinum is a good metal, then at room temperature it has low resistance. To reach 0 degree temperature, we need to decrease our room temperature. Then how platinum has such high resistance at 0 degree Celsius?
Okay. See, one thing is that platinum, if you have a wire, what I am talking about platinum 100, that is a wire. Okay. If you reduce, that will be more scattering. Okay. It may not be continuous also. That will be hopping. So that adds to the resistance. I am not denying that.
1000 ohm is very, very.
Yeah, but if you reduce the thing, you will see.